Hey, this is Horner, and this is the 2015 AP Physics C Mechanics Free Response question, number 2. And this one deals with a ballistic pendulum. So we have a small dart. It is shot out of something, and it is launched at an angle of 30 degrees. It comes up, it hits this block, it sticks in the block, and it pushes it over to an angle. So pretty simple problem to do. Really like these because they combine both energy and momentum. So you just have to be careful about what's conserved and when it is conserved. So the very first thing they want us to do is find the speed of the dart just before it hits the block. So obviously we've launched this thing at an angle. We know that our angle here is 30 degrees, and we want to know what is the speed of this thing. And notice that at this point it is entirely horizontal. So it is launched at an angle, but we just want to find that horizontal part. And so it does tell you that it is at the top of the path, it is moving horizontally. So they've made it easier that way, I guess, if you want to think about it. So we know that our velocity v is here. We want to know the bottom of this triangle, of this little guy here. Let's get rid of that funky little box that keeps showing up. There it goes. And we want to know what is the bottom, so we're going to do v times the cosine of 30 degrees. So the velocity in the x direction is equal to the original velocity times the cosine of 30. Our original velocity is 10 meters per second. We're going to multiply that times the cosine of 30, and we end up with 8.7 meters per second. So it's pretty easy. All that work is worth 1 point. You need that, though, for the rest of the problem. So for the next thing, they want us to calculate the horizontal distance between the launching point of the dart and a point on the floor directly below the block. So that is this distance d right here. So let's go through and do that. We know that the final velocity in the y direction is equal to the original velocity in the y direction plus acceleration in the y times time. And the reason we're doing this is we have to find the time in order to help us find the distance. So we know the final velocity at the top in the y direction is 0. The original velocity is going to be 10 times the sine of 30. Why is it 10 times the sine of 30? Because we're worried about the velocity going up and down, which is right there. We said that this is 30, we know this is 10, so this side is going to be 10 sine of 30. 10 sine of 30, and then we're going to add to that the negative 9.8 or negative 10, up to you, times time. And so our time here is 0.51 seconds. If you use 10 for g, you're going to get 0.50 seconds. So there's really not a big difference, and they make sure of that. We still haven't found what we want, and that is the horizontal distance d. To find that, we know that position, or d, is equal to the velocity in the x direction times time. Remember, that comes from vx is equal to d over t, or d is change in position. You can think of it either way. So we're looking for d now, and this is going to be equal to our velocity, which we found earlier, of 8.7, and we multiply it times our time, and we end up with about 4.4 meters for that distance. Next thing they want us to do, is such a great little easy problem, is calculate the speed of the block just after the dart strikes. So we know that the original momentum should be equal to the final momentum. So here we've got m1 v1 original is equal to m1 plus m2, where that is the projectile is 1 and 2 is the block, times the final velocity. So this is going to be 0.02 kilograms times 8.66. And then that's equal to the mass of the the mass of the, that's of that projectile plus, or the dart, plus 0.1 kilograms. And we'll multiply that times VF. So VF here is equal to 1.4 meters per second. Next thing they want us to do is calculate the angle through which the dart and block on the string will rise before coming to rest. So this is just kind of the going backwards and finding angle instead of finding that original speed. So this is the angle theta. I really didn't give a lot of space here, so we're going to try to space this out a little bit differently. First thing we need to do is find the energy here. So we know we have kinetic to begin with. We know that in the end we have potential energy due to gravity. That is 1/2 mv squared is equal to mgh, and our height here is equal to L minus L times the cosine of the angle. Where did that come from? Remember, for a pendulum, here is where it starts height-wise. It will come up to here and it will stop. So that's our new height. Our angle theta is here. If this is the entire length and that is the entire length, and this side of the triangle, okay, so right here for this triangle, let's change colors because I think that will help us see that just a little bit better. So we're going to go in and change colors. So we'll go to blue. So now we've got this side of the triangle is what we want. Here is our triangle. That's the angle. So this will be L times the cosine of the angle. So h, which is this distance right here, from here to here, h is equal to L times 1 minus the cosine of the angle. There we go. So now we're in blue. Hopefully that's okay for you. We'll go back to our equation. 1/2 mv squared is equal to m times g times, and then here we've got L minus L cosine of the angle. So I put everything back together again. Hopefully that's okay. I'm going to take it up. Well, let's leave it apart. So this would be mv squared is equal to, and then this is mgl, and then this is 1 minus cosine of the angle. All right, so now that we have that, let's solve this whole thing for the cosine of the angle. So the cosine of the angle is going to be equal to 1 minus v squared, so there's our v, over 2 times g times L. Our m's did cross off here, which is really kind of nice. If they didn't, that would be a problem. Now we're going to plug everything in. So now we've got cosine of the angle is equal to 1 minus, and then our velocity is 1.44 from earlier. We have to square that, divided by 2 times 10 times 1.2 meters, and we will end up with an angle then of theta 24 degrees. So we did have enough room there. So the block here then continues to swing as a simple pendulum. So they want us to find the period. This one really is not bad, so we're going to go ahead and do it even though it's not part of momentum or energy. So period for a pendulum is just equal to 2 pi times the square root of the length of the pendulum divided by g. So this is equal to 2 pi times the square root of, we said the length is 1.2 meters, gravity is about 9.8, so this will give us 2.2 seconds. To find the time, then here, the time between when the dart collides and when it returns to its original position. So this is only swinging from here up and then back down to here. So it's not a full swing. It's just part of, it's really half of a full swing, because remember, a full swing would start here, come all the way down, and then come all the way back. So we only have this part of it, so that's only 1/2 of the period, or 1/2 the time. So in order to find the time, that's equal to the period divided by 2. Our period is 2.2 divided by 2, and that gives us 1.1 second. In a second experiment, the dart with more mass is launched at the same speed and angle. The dart collides. They want to know, will the angle theta that the dart and block swing to increase, decrease, or stay the same? It should increase, and they want us to think about that. And so probably the easiest thing to say would be a more massive dot would cause the speed to, with the block, to increase. So more mass, the speed after the collision would be greater. Oops, would be greater a greater speed, so a greater velocity here, would cause an increase in height, and that would then increase the angle. So as long as you kind of say, we're going to start with mass, that changes the speed is bigger, that causes the height to be higher, and therefore the angle is bigger. You couldn't just say, well, the speed's faster, so that way the angle's higher. That wouldn't work. You'd have to be really careful there. For the next one, would the period of oscillation increase, decrease, or stay the same? It would stay the same, because if you think about our equation here, t is equal to 2 pi square root of L over G, and so no mass at all here in the equation, so therefore mass will not change it.